And welcome. There is one more problem on the screen, and in this problem, what happened to the soap bubble? It simply sticks to the tabletop. Oh, the problem is we blow soap bubbles over a horizontal, wet. Oh, tabletop is wet, so friction is not there. Wet tabletop. One of the bubbles, 4 centimeter in diameter, sticks to the tabletop, and after sticking, it took the shape of a hemisphere. Okay. What will be the diameter of a hemisphere? I don't know whether this is hemisphere or not, but this took something like some shape like this. What will be the diameter of the soap bubble after then? Oh, so I'm gonna think the pressure in the bubble, it is stick. The pressure in the bubble is same of the external air pressure. Yeah. Yeah. Uh, since the air pressure is same both outside and inside the bubble at all parts of the surface, the curvature pressure must be the same at different parts of the sphere. That is why a freely floating soap bubble takes on a spherical shape, since the curvature of the spherical surface is obviously constant due to the symmetry. And according to the same reasoning, that means we are going to use it. The bubble stuck to the tabletop is also a surface of constant curvature. So it must be some part of the spherical surface. So the problem is, what is the angle alpha between the tangent of the spherical cap and the plane of the tabletop? That is the angle alpha. And the answer, I think, is the small piece of soap film in contact with the table is pulled by the rest of the film in the direction of contact plane. On the other hand, is point P. We know that the point P of the film can easily move horizontally, since the wet table cannot exert a horizontal force on the table. Friction is absent. Therefore, the contact plane of the film at point P must be vertical. Yeah, that means alpha is going to be 90 degree. That means alpha is going to be 90 degree. That means the bubble is hemispherical. That why was right, I guess. And the curvature pressure, that is the pressure difference created due to the surface tension of the soap bubble, is small compared to the external pressure. So the air pressure is practically same as the atmospheric pressure. Therefore, neither pressure nor the temperature of the air in the bubble stuck to the table changes. So its volume remains the same. And the volume of the sphere is same as the volume of the original bubble, because nothing has gone in the air. So its diameter is volume 4 by 3 pi r. So its diameter is something like this times the diameter of the sphere. And that is the answer. That is the question I was asked. Bubble diameter was given, and the soap bubble diameter will become like this. And I solved the problem. Thank you very much.